Good morning, all of you. So today's class we are going to discuss about the X-rays. It's a very small topic. It's there for both for mains as well as for advanced. It is there. In NCERT book, there is no description of X-ray. There's no chapter, but still it is the part of syllabus. Fine. So I'll start with the Coolidge tube apparatus. Okay, as we know, historical background, like when when a light is incident on a metal surface and it will eject photoelectrons. And these electrons, they'll have energy ranging from 0 to K max here. Now, can we think about the reverse phenomena? If a fast moving electron beam strikes a metal surface, do we get that EM wave? Is what happened that they were trying to search that one, and accidentally what happened? A German scientist called Ronton. So what happened? He was doing some other. He was studying the cathode ray tube, means cathode ray CRT it is called as prior to the old television, means like what I watched television, they were cathode ray tube. From cathode ray tube televisions open, we came to LCD, liquid crystal display televisions. Then from that we went to plasma TVs. Then we are in the era of the LED TVs. That one. What I used to view, it was like a cathode ray tube. The televisions clarity will not be there that much, and minimum what happen, you should maintain some distance. You should be at a distance of say at least 2 meters. If you go nearer, no, you can't see anything properly. It was having its own drawback, and it used to get eat up. After I think 2 hours, we used to switch off. We used to give. Sometimes the television used to stop working. I'm talking this in 1984, 85, 86, like that. After 1.5 hours, we used to switch off it. We used to make it cool, 10, 15 minutes. Then again, we used to restart. That was the problem with the cathode ray tube thing. So then, so when the Ronton, when he was studying the cathode ray tube, means when electron beams go and strike some screen, what conditions will come? Then the electron beam used to make it incident on some metal surface, then used to watch what will happen to that one. And these EM waves, X-rays, what X-rays are EM waves? They're invisible, no? So I think he never noticed. So these X-rays, after getting this particular EM waves, or what you can call X-rays, when they went and somewhere in his lab, there was some photofluorescent screen. What do you mean by fluorescent screen? If there's a screen, here I'll give a coating. Zinc carbide, like this different, or phosphorus, zinc, that one. If fast moving electron comes and collides, if a fast moving electron comes and collides here, then the kinetic energy of electron weapon will be reduced. Sudden decrease in kinetic energy, that what will be converted into EM wave, and that will be absorbed by the phosphorus atoms. They'll jump to higher state. When they again come back to the lower state, they'll give out photon. And that particular photon, what happened, will be there in the visible spectrum. And we are able to see the light. This was the earlier televisions, what we are using, CRT tube televisions. This was what we are using. Got the idea? So this was all the display instruments what we were using earlier. That one. So he was interested to study that particular thing. Then accidentally happened, there was a photographic plate, or the fluorescent screen was somewhere far away. And you notice that there is some sort of like a displays are coming. Then next again, there was a photographic plate, and he saw some marks in that one. So why do this marks has come some from? I didn't never sent any rays here. Then as the state made observation, then finally what he came to, there is some radiation coming from metal, or you can say target, when fast moving electron beams are coming. He don't know what to call them. He called as X-rays. Later, when they measured wavelength, they came of order 1 angstrom to 100 angstroms. The wavelength of X-rays, it was around 1 angstrom to 100 angstroms. Not clearly defined. Different books they're telling 1 angstrom to 100 angstroms is what you can call them as X-rays. Wavelength of this order. Wavelength of this order, you can call them as X-rays. So like that, what happened? The idea of X-rays came into the this I think SC Verma will follow it. 0.1 angstrom It's a EM wave, not lies in visible spectrum. Definitely, I think visible spectrum 4,000 to 7,000. So nowhere in that visible spectrum. No. So such a thing, what happened, they're called electromagnetic waves here. So what is the basic idea of this? Fast moving photographic plate, which will block certain light, amount of light, and particular what happen, it will form an image. What is a X-rays? X-rays is what? When fast moving electron beam is incident on a target or a metal, then due to retardation of that, electromagnetic waves are generated. And that electromagnetic waves only we call it as the X-rays here. So here only I think, let me put it. So if this is a metal, now we'll make electron beam incident on it. Don't call them photoelectrons. Need not know. I can produce electrons by many methods. Then the resulting spectrum is what? We'll call that as X-rays here. Or say photons. There's a basic idea of the principle of this particular X-rays here, fast moving electrons. Next question comes. Any moving electron, if it undergoes retardation, should produce X-rays. Then electron was also moving in current intensity chapter, no? So will I get there X-rays? The answer is no. Fast moving electron beam. So strict condition is what? Fast moving electron beam, if it encounters any metal surface, then an X-rays are produced here. Don't just say that moving electron strikes metal surface. It must have sufficient kinetic energy. So you may directly straight away say, is it really possible? I think you do one thing in the night. You take a big boulder. So this will be boulder will be there, no? Big rocks. I think you might have noticed this. This will call boulders, sir, not rock. You take small rock, throw it, just to drop it here. Say some height of 1 meter or say like a 0.5 meter. You don't get any spark here, no? Then instead you stand here, far away, and throw the rock with a certain speed. So with a high speed, that one. Then when it goes and strikes, you'll get a spark. You get some light, no? Here, when this comes and strikes. Is it fine? So, but instead, if you just drop here, if you just drop it, you don't get anything. It'll go and strike, inelastic collision occurs. Now also happen this particular rock, what happens when it goes and strike this boulder, when you throw with high speed, you will get a, I don't know nowadays you played or not, we used to play a lot. We used to be a little bit far. If you are nearer, what happen, the rock, what happen will break up and pieces may strike you. You have to be very alert, that one. So when you, so there's a very important, I think in a simplest way, I'm just giving example like, sir, how it is possible EM waves that particular, what you see in the visible spectrum, maybe the velocity with which I'm thrown, the EM waves are produced is of order what? 4,000 Armstrongs to 7,000 Armstrongs. If I further increase the velocity of the throw, if I increase the velocity of projection, maybe what when the EM waves produced will be less than this, I'm unable to see. If I decrease velocity, maybe the EM waves produced may be greater than 7,000, which will be not in visible spectrum, I'll not see that one. So when you throw a particular rock, don't take big rock because again you have to project with something which you can hold in your hand. Throw hard against any big boulder that you can see in the night. In the night you can see that particular spark here. So what is the reason for that? This fast moving rock, it was having kinetic energy. When it encounters collision, it will become inelastic. And here what happens? The energy is suddenly released in the form of visible spectrum and we see light here. The same thing happens for the electron beam also. So how to produce that electron beam? Let's come for this called like a Coolidge tube. This called like a Coolidge tube. So what is this? This called like a glass envelope, evacuated glass chamber. I'll give some. So what is this? This is like a glass chamber made up of glass, evacuated glass chamber. What all particular air is there? I'll evacuate it. I'll remove the air. Then there's the both thing. Next again, there's a filament, or you can say like a filament or electron gun. You can call that as electron gun. That one. So what actually happens? It will send electrons. Okay, a current I will flow. How the current, filament current should flow like this, no? Because the electrons will flow like this. There's a filament current. Small I, let me write. There's a filament current, and how the electrons will move in this direction. Show like this, so it'll be easy for you to understand this one. So these electrons, what happen when they pass through this filament here? Thermionic emission occurs here. Due to thermionic emission, why thermionic emission? Because when a current flows through a conductor, any metal or a conductor, heat will be generated. Due to heat generated, there the heat generated is sufficient where the electrons, the kinetic energy of electrons now, the thermal energy of the electrons will be such that it will be greater than work function. Then the electrons will be ejected from the surface of metal. These electrons open using a magnetic field. So because they'll be spreaded like this using with the help of magnetic field open, I will make them oriented in the form of electron beam. Now this beam, so here what happens, this beam will be accelerated because you see this one. Now come for this red color wire I'm showing. So there's a positive potential, negative potential. So in what direction there should be electric field? In what direction the electrostatic field? Okay, this is a negative, positive. So the electrostatic field will be produced by the accelerating potential will be in this direction. Then any electron present here, in what direction will experience a force? A field like this, and it will have kinetic energy. I'll show one electron here. And now look at this. You come back to electrostatics. This end is positive, no? So this end is made positive. This is negative now. So electrostatic field is set up. Who will set up this E? The accelerating voltage. Look at the potential: 20,000 to 100, the 1 lakh volt. 20,000 to 1 lakh voltage. Such a high potential difference is what generated, and very high electric field will be present. This high electric field, what it will do? It will accelerate these electrons present in this electron beam. So what is this? Fast moving electrons, or what is this? Fast moving electron beam, because that's what I needed, no? So what is the duty of this filament current? If I increase this, current will increase, the number of electrons will increase, or current will increase, more heat will be generated, more heat generated, then more electrons open will get sufficient energy, then what happen, more electrons will come out of this one. So if I want to increase the number of electrons in the electron beam, so tell me what I should increase the filament current. Got this one? Next again, I want to increase the kinetic energy of electron beam. Whose help I should take? Accelerating voltage. So what accelerating voltage does? Controls the kinetic energy of controls the kinetic energy of electrons. Fine. What about the filament current? What it does? This will be controls the number of electrons emitted. By varying this EMF 0 to 10 volt, I can vary filament current. From filament current, I can control the how many electrons will be ejected per second. So like that, what happens? By varying filament current, I can control number of electrons in electron beam. By varying exciting voltage, I can control the kinetic energy of the electron beam. This is the overall setup here. With the fast moving electrons, they come and strike the target. What is the basically target? Usually what we use target will be the very popular target, tungsten or molybdenum. These are the very popular targets which I'll be using that one in general application. So what is the target made up of? Target, it will be tungsten. Or I'll go for what, like platinum. Many different metals are there. So these are the very popularly used target material. So there's a target. So what is the target? It's a metal, no? So there's fast moving electrons. Now what happen? Will encounter collisions inside the target. And when it encounters the collisions there what happen? The kinetic energy get decreased. The decrease in kinetic energy what happen? This is the orbits of the target called ZD, and there's a fast moving electron beam. Now the moment it enters, this will be the path. Now these are the orbits, so we will show that electrons. And like this, you can show the electrons. This will be K shell, L, M. Let me leave it like this. K, L, M, N, O. You can show the shells here. This is what fast moving electrons. Why do excess? How excess will come? I'm showing one atom. There's a target atom. So when this electron it moves here, it will undergo retardation. So how it is possible? Where is the retardation? I'm not seeing. So why do it get deflected? First of all, say like a electron. There's electron and there's a proton, no? Because inside the nucleus the proton will be there. Then will it exert any force? Yes, because it was having a velocity v here and the force. So what will happen to the particle now? It starts deviating. Or I think I'll show it here. Just will show in this direction. Rough diagram it is. So there's a fast moving electron, that one. So here the proton will exert a force, no? Due to that, what happen? Better you say it will undergo retardation here. So when it is undergoing retardation, so what it will do? It will give out continuously radiation. I think I'll start from here. Continuously it will undergo resistance. There will be opposition and it will give out a radiation. I'm just giving rough diagram. We should not discuss motion of the electron with respect to one atom. Altogether, it will see the block. It will see some sort of a volume of a conductor. So actually, everyone, what happened? You can also put better like this. There should be. If I come like this, it will come here. So that since I drew diagram here, that's why I'm just showing it here. It will come like this. You can this one. And now what is this? These green colors are what? X-rays. Continuously what happen? There means is it all the energy of the electron will be converted into X-rays? No, the answer is no. So most of the 90% of the kinetic energy of electron will be converted into heat, The remaining what pen will be converted into X-rays here. Sir, why do this X-ray? Again, still like a, why do this X-ray means? Again, you go back to, please do listen. At the end of, you can ask question. At the end, you can ask question. No, no, not needed to ask. First, you listen. I'm starting it. You can't ask any question. One may say that, okay, this what happened. Then in the end, you can put questions. Huh? Please, in between what happened? If you ask questions, then I have to get deviated instead of main topic. What happened? Other all unwanted questions. What I have to answer. No, this particular electron. So why do this X-ray? Again, I asked you to remember, go back. If a rock, if you throw a rock with a high speed against a boulder, what do you get? You get that light energy. Why would you get light energy? Because that electron weapon will encounter almost like some inelastic collision. No? So like that weapon, this particular electron now it's not moving in an atom. Better you say that it is moving in a metal. And what that metal, because of crystal lattice structure, the atoms will be closely aligned and the electron has to penetrate to the material. Penetrate to the material. So there'll be a resistive force. And since it is not moving with a low speed, it is moving with a very high speed. So all of a sudden energy released. That energy weapon will be in the form of what? X-rays. This is the core idea of this X-rays here. All of a sudden energy released, not like because this electron has to move inside the material of the target. So it should penetrate through that one. So then what high resistance will be offered. 90% will be converted as heat, only 10% will be converted into X-rays here. Sir, why that heat will come? Due to, you can say again resistance. Why that X-rays? Why that X-rays? Because sudden decrease in kinetic energy will lead to X-rays here. Sir, also there is a resistance to the flow of electron. Yes, that will be heat. Both will occur here. A part of kinetic energy will convert into heat. A part will be in the form of X-rays. Why not only heat? Because here sudden decrease in kinetic energy will come. Means all of a sudden it will leave out as few electrons will give out all its kinetic energy in the form of X-rays only. Few electrons what happen? Will give out all its energy in the form of heat only, and that number is very few, and there are few electrons what happen, they'll give their energy in the form of heat as well as X-rays. Sir, why it happens like that? All electrons are having same kinetic energy and all are having same mass and the same target material? Question mark. The Newtonian physics or classical physics, what we know, we cannot answer. Then quantum mechanics. Say every topic, say there's a rule here. Every topic you should end up with question mark here. So there are three categories of electrons are there. One set of electrons, when they enter into target material, they will give out all their kinetic energy in the form of X-rays. Got it? Next, another set of electrons are there where like their kinetic energy, a part will be converted into heat, a part will be in the X-rays. Then next, another set of electrons are there where their particular kinetic energy, most of them will be in the form of heat. Most of the energy will be in the form of heat, that one. So you can put three kind means, sir, will there be any like a X-ray with infinite wavelength? Don't say infinite, very large wavelength. Very large wavelength, because 99.99% will be heat. Very small fraction what pen will be converted into what? Into the X-rays here. So therefore, what do we get? We get X-rays of almost very large wavelength also here. This is what happens here. So like that, what happen? A continuously, this electron, say one electron, sir, how many photons it will leave out? I am showing it very clearly. 1, 2, 3, 4, 5, 6. There can be another electron where it will give out only one photon. There can be another electron what when which may give only two photons. So like that, as the electrons are passing through material continuously, what happen? We'll get a X-rays here. So if I plot that spectrum, so I'll call that as a like a continuous X-ray spectrum. So how the curve like a continuous X-ray spectrum. So how the curve will be some peak. like this. So don't show intensity zero. So I'm plotting this is intensity, and this is a wavelength. And don't make it intersect. They just leave this curve. Lambda infinity should not be there. Very large wavelength it will be that one. Now you can see that what is this particular. What do you mean intensity? Intensity of X-rays here, not intensity of anything. Intensity of X-rays, nothing but photons. So now what happened? There are some photons which are generated which will have maximum energy, and next again there are some group of photons where their number will be maximum, and next we do have some set of photons where the wavelength is almost very large, but what about their number will be very less. Why do the curve like this only? We don't know. We can't give reason with the like a physics what we know it. We have to stop it, and this is called like a cutoff wavelength, or in the books what happen they call lambda naught. And we have this particular where for particular wavelength where the intensity is maximum. Then who will determine this cutoff wavelength? Lambda naught, and this called like a continuous spectrum. We call it continuous spectrum, that one. Which particular electrons? Yes, all electrons are responsible for this particular thing. And this is the basic thing. So this lambda naught is called as cutoff wavelength here. So who will determine that lambda naught? So now, so who will produce that lambda naught? There will be one group of set of electrons. What happen? Where the whole kinetic energy of electron open will be converted into X-rays. The whole kinetic energy get converted into X-rays means then what is the kinetic energy of electron? Should be called SC by lambda naught. And what is K max? EV naught. What is V naught? Accelerating potential. That I'll give symbol here V naught. So what all the kinetic energy? K max you call it. All electrons almost will have same speed. The K max, what happen where one electron, so few set of electrons, the whole energy of electron will be converted into X-rays here. So how it is possible? It happens. I think so like the physics what we know we cannot give any reason. Just leave it. Question mark we have to end up here. So now this EV naught I'll equate this one. So EV naught equal to SC by lambda naught. So what is lambda naught? SC by EV naught. So who will determine the cutoff wavelength? This much. Means there is some cutoff is there. Why do this cutoff? Why can't be zero? No, there's a maximum permitted kinetic energy of electron. No? We cannot get electron in electron beam greater than this. So when the whole energy of the electron get converted into photon, will get converted into X-rays, then that happen, that cutoff wavelength will come. What about their number? Their number is very less. And next again, we do have some set of electrons where their energy what happen will be converted into X-rays here. And what about their number? Maximum. And next we do have some set of electrons where their energy will be converted very less into electromagnetic or X-rays here. Why do the curve like this? We can't give reason. Why do? Because all electrons are same, no? This filament, will it produce electrons of different nature? No. This particular filament, what is the filament? Made up of some copper, aluminum. In copper, all different electrons will be different nature, nothing. All will have same mass, same charge, same spin, everything will be same. So these electrons will be ejected. What is the nature of all these electrons? Will be same. But still what happens? We do see like this. So it's a question mark. Just leave it. It's not part of thing. We have to enter into quantum mechanics. Got this? So why do that cutoff is there? We can't give reason, but there is a cutoff. And we don't get any photon whose wavelength will be less than this cutoff wavelength. And now I'll increase the potential V naught. I'll decrease this. I'll decrease the lambda naught will increase. If I increase this, lambda naught will decrease. So therefore, if I plot for different accelerating potential, so how the curve will be? The curve Let me go for the graph. This particular curve you have come across somewhere. Go for radiation chapter, Wien's displacement law of X-ray citizen, and this is the wavelength. The cutoff wavelength will come. So this will start with some 20 kilovolt. So when I plot this one, and you look at the wavelength for which intensity will be maximum, and also look out for and the cutoff wavelength. So you call this is lambda 1. So as I increase the accelerating voltage, then what will happen to cutoff wavelength will decrease here. And what happened to area under the curve will increase. I think it's quite clear, no? If I increase the accelerating potential, this, why do the area under the curve will increase? I think I can't bring. Okay, let's have this one. No, I'll increase the accelerating potential. Why do the area under the curve should increase? Okay, let it be like this only. Maybe what when you can just shift this particular graph here only. But why we should increase this area under the curve? So as I increase the accelerating potential, what will happen to the overall energy of the electron beam? Number of electrons, let me make it fixed. No doubt. I'm going to make number of electrons fixed here. The filament current constant. I'll increase the accelerating potential. So as I increase the accelerating potential, so what will happen to the number of total energy of the electron beam will increase. Total energy increases, definitely what will happen? They'll penetrate more deep into the metal, more deep into the metal. Then what happen? More resistance. So definitely what happen? The more photons will be given out. More photons are given out, then intensity will increase here. So therefore, as you increase the accelerating potential, the area under the curve will increase. This is similar to where thermal radiation, Wien's displacement law, and what happened to cutoff wavelength will decrease. This is very important. In exams, till now they didn't ask possibility of asking because in syllabus we have only this much, but they may ask you here. So for higher accelerating potentials, the area under the curve should increase. Any reason for that? Because the total energy of the electron beam will increase. So more energy means what will happen? They can penetrate more. If they penetrate more, means you can see that one. If it penetrate more into the metal, then more photons will be given out. So the energy on the curve, number of photons increases, intensity increases. Like this, the lambda m, I'll write it. What is lambda m? The wavelength for which intensity will be maximum. How this lambda m will be related by this particular formula. The wavelength for which intensity is maximum, that is related to cutoff wavelength by this particular thing. This derived in quantum mechanics. Possibility of asking, not there in our books, but still they can ask you, what is lambda? The wavelength at which intensity will be maximum. So this is about the continuous spectrum. Why continuous? Because continuously what will happen? Electron moving inside the target material will encounter resistance due to the target material, or better you say retardation here, due to retardation. Then it will give out the energy in the form of heat as well as the like a photons. That photons is nothing but we'll call X-rays here. Now these X-rays are EM waves. And next, as I said, 90% will be converted into heat. So what will happen to the target here now? It will get heated up. Then the heat generated may be such that it may melt. So therefore, what type of target I should pick up? I should pick up a target where it should have high melting point. Example is tungsten. So why tungsten is preferred? It's having high melting point. So what is the basic requirement of target? It must have high melting point and high atomic number. So the requirement for target, high melting point. Next, higher atomic number. These are the two requirements here. So why the target should be made like a high melting point? Because 90% of electron beam energy is converted into heat. So therefore, a lot of heat will be generated. So to absorb that heat, what I do, I'll take a copper rod. Why copper is preferred? Because it can absorb heat very, it's having very good thermal conductivity. So the copper weapon will absorb that heat from the target. And I'll pass a water through the copper here. I'll make a channel like this. If I send a cold water, then I'll get a hot water. So what I should do, for every 1 minute, 4 liters of water you should send. That much of heat will be generated. For every 1 minute, 4 liters of water should be passed out. What is the temperature? Suppose I think usually around 25 degrees you take it. The water what I get is around 50 or 60 degrees Celsius. It depends upon for what time. For every 1 minute, 4 liters of water you have to push. And the temperature of cold water entering will be around, so like a 20-25 room temperature. This will be around from 40 to 60 degrees Celsius. So like this, what happened? This particular, the temperature of the target can be minimized. That's why it is called like a Coolidge tube. I had to do cooling. I had to do the cooling particular thing. Okay, now after this, now the electrons, what happened? This like this, the filament will continuously lose electrons. No, it's a big problem. These electrons, what happen, will be attracted by positive terminal of accelerating voltage. So the same electron had to show it here. Are you getting the passage? I'll magnify it because once we'll discuss this, this will be easy for you. Yeah, see. So these electrons, now what will happen? They will propagate like this. And they will enter the Coolidge tube. So I think I shown red and blue color. This is very important. Same electron only, just since it will be like this. So what is the path of electron? The electron, what happen? Emitted by negative terminal will pass here. So here what will happen? The filament will lose electron. That electrons will go in substitute here. These electrons emitted will be excited by potential high speed electron beam. When they strike target, heat will be generated and the remaining part X-rays. These electrons open will be absorbed by the positive terminal of exciting voltage. It will come like this. Now this particular electron again then from negative terminal, so it will flow like this. So as it charge is conserved, Coolidge tube apparatus will obey law of conservation of charge principle. Yes. In what direction there will be current? You have to show that current here like this. Shall I call that filament current? Call this is filament current. Give name like this. It's called like a filament current. So that same I is what flowing. And what is the power of the Coolidge tube? Shall I say exciting voltage into filament current? And what is the efficiency of this? Very good efficiency, that one. But sir, you said 90% heat generated. Yes, I'm not bothered about that heat. So what I do is I can control that efficiency. But altogether, what happened? The energy of the electron beam, what happened? 90% will be lost as heat. Only 10% will be converted into the X-rays here. That is enough for me. That is enough for me, that one. So what is the power of Coolidge tube? Power of a Coolidge tube. Accelerating voltage into filament current. And numericals, I think this is going to help us a lot. So what is the exerting power of a Coolidge tube? You write it P V naught into I. You will just put it like 80% of power is lost in the form of heat. So remaining how much is available? 20% is available. That 20% will become the power of the X-rays. So there is possibility of that one. Asking any questions. Okay, now let's come for this one. And now if I increase the filament current, number of electrons will increase, no? More number of electrons striking target. Then what will happen? More photons will be generated. Then what? More photons means what will happen to the spectrum? Intensity of X-ray increases. So therefore, shall I control the quantity of X-rays? How to vary the intensity of X-rays? Don't say that, sir, I'll vary the accelerating potential. Accelerating potential. So how to increase the intensity of X-ray? Just increase the filament current. Increase the filament current, then intensity of X-rays will increase. Now, if I increase the accelerating potential, if you increase the filament current, what will happen to cutoff wavelength? Will not change. Are you able to analyze here? Cutoff wavelength will not change. Are you looking at this? The lambda naught depends on V naught here. So if you increase filament current, intensity of X-rays will increase. So you may get curve like this here. Let me plot that graph. I need some pages, extra pages will be it. No, let me go for increasing the filament current. What will happen to the cutoff wavelength? It will remain as it is. Then slightly it will increase, not something like a, will be like this. And the peak at which intensity is maximum, that will remain as it is. Only thing is I'm increasing the intensity. The cutoff wavelength will be as it is. So this is for call I2, this I1. It's not intensity, current, filament current. So by varying the filament current, what we can control the intensity. Shall I say intensity means quantity of X-rays? And next, by varying the accelerating potential. If I increase V naught, then what I increase? I'll increase the kinetic energy of all the electrons, Then what will happen to the, you look at this one, as you increase the accelerating potential, tell me what will happen to the wavelength of all the photons? Will increase. So shall I say more energetic X-rays? So if the X-rays are having lesser wavelength, you can see more, if you look at this wavelength, this photon and this photon. This photon is having more energy, no? If it's having more energy, more penetrating power. So like this, shall I classify now hard X-rays, soft X-rays? What do you mean by soft X-rays? Less penetrating power. Hard X-rays, more penetrating power. So how to control the quality of X-rays? Quantity means number of photons by varying filament current. Then how to control the quality of X-rays means penetrating power. So as you increase the accelerating potential, lambda naught decreases. Then what will happen to the given, now what happened? I'll get more energetic, the number of energetic photons, then number will increase, no? You look at 20 kilowatt, 70 kilowatt. What happened? More energetic photons are available here. So what about the energetic photons only in this region? Now, when you go for 70 kilowatt, what happened to more energetic photons? They're available here. So don't bother this. Answer like a 20 kilowatt, 50 kilowatt. Look at this. Their energy is same. Look at this part. Look at this part. Here you see that more energetic photons. What happened? More energetic photons has increased. So therefore, as you increase the exciting potential, so what will happen is the quality of X-rays can be varied. Quality means penetrating power of X-rays I can increase here. So soft X-rays, hard X-rays. What do you mean by soft X-rays? Less penetrating power. Hard X-rays, more penetrating power. So exciting potential will control the quality of X-rays. Filament current will control the intensity of X-rays. This for the mechanism is what I just developed here. So got the idea, no? So this is about the continuous spectrum. The overall picture is what we have developed here. Okay, now one more very important parameter is going to occur here. One more important phenomenon is occurring. This fast moving electron beam. Let me show like this. It will be easy for us to compare. This is the intensity. This is the wavelength. Cutoff wavelength will be as it is. This is you call atomic number Z1 or say Z2, Z1. Z1 will be greater than Z2. So why the area under the curve increases? If atomic number increases, what do you mean by that? More electrons, more protons. Then what will happen to in a the density of that one will increase. The atoms will be more closely packed. Then what will happen to this particular electron, fast moving electrons? It will encounter more resistance, more retardation, more photons are given out. More photons are given out, intensity will increase. Has shown big gap, slightly slightly Z1, the green color will not overlap with Z2, will lie just above. Cutoff wavelength will not change. This graph is very important. In other books, they are shown wrong. And Surma, you didn't discuss that one. So if atomic number, if they, what is Z1, Z2 of target? So where is Z1, Z2, you have to write for target. Here you write it, Z. So it's a target nucleus, no? What is this target atom? Z is not of filament. Z is not of filament. Z is of target here. Atomic number of target. Okay, I agree this one. So as you increase atomic number, so what happen? The more densely, what happen? The atoms will be packed in a given volume. And because of that, the electron will encounter more resistance, more retardation, then more photons. The intensity will slightly increase. This is a curve. Just do remember. No, cutoff wavelength will not change. Cutoff wavelength depends only on exciting potential. Now let's come for the properties of X-rays. What are like, okay, after studying all this much X-rays, everything, let's concentrate on the property here. Now, one by one, let me summarize things. They'll pass through many materials more or less unchanged here. It all depends upon the, again, the type of X-rays. If they're hard X-rays, they will have more penetrating power. They'll penetrate more into the material. Soft X-rays. Suppose say, I want to scan the lungs. So what type of X-rays I should prefer? Soft X-rays. If I want to scan the bone, what happen? At least it should happen. It should penetrate more, no, little bit into the bone. So like that, depending upon like a what you want X-ray of the bone or of a tissue, no. Based on that, what happen? I should control the what? I should control the exciting potential. From that, what happen? I can control the penetrating power. From penetrating power, I can go for it. No, they cause fluorescence in materials such as rock salt, calcium components, or uranium glass. Means like when these fast moving electrons, so when these X-rays, they are incident on some substance, they'll show that particular thing. Fluorescence is what happens, they'll produce a spark. Next, they affect photographic plate, causing fogging. I think that's what we use in X-rays, no? So what is the photographic plate? A layer will be formed. When these X-rays go and collide, no, that particular layer will be disturbed. Where the X-rays are incident on that one. Hmm? So just have an idea that one. They cannot be refracted. Any reason for that? Because they are very high, low wavelength, no, very high frequency. If I pass through a glass, will get refracted? The answer is no. The reason is high frequency. Visible spectrum will get refracted for the glass, other thing. So high frequency waves like X-rays no cannot get refracted. So there's a property of EM wave. Just have an idea, information only. They're unaffected by electric and magnetic field because there is a EM wave, no. So photons will not get deflected by electric and magnetic fields. Then they discharge electrified bodies by ionizing the surrounding air. when these photons, when they're passing through any medium, gaseous medium, what they do? They'll encounter collision. If I pass these X-rays through hydrogen gas, as the hydrogen gas will get excited. That's what the meaning of discharge here. They discharge electrified bodies by ionizing the surrounding air. This is what happens. They can ionize the air, that one. They can cause photoelectric emission. If these X-rays are incident on a metal, they will produce in turn photoelectrons. They are produced when a beam of high energy electrons. Okay, this already we have discussed here. Again, we have a soft X-rays. I think already you know soft X-rays, hard X-rays, then high intensity X-rays, low intensity X-rays, how to generate, we have discussed that. This is about the overall picture of continuous X-rays. Along with this, there's one more phenomena is occurring. Okay, some of you are asking, sir, this electron will not interact with valence electrons. What are these? Valence band. These are valence electrons, no? So what will happen? So this electron in its path, will it encounter any valence electrons? Yes. There's all probabilities there. So when this fast moving electron collides with this valence electron, what it will do? It will dislodge, it will knock out that valence electron. So can it happen? Yes, it can happen. So when this fast moving electrons in its path, if it encounters any valence electron, yes, then what happens? It will knock out that valence electron. It will knock out that valence electron. So here I'll just show it. When the fast moving electron beam, fast moving electrons, so when during its path, I'm just showing straight line. Actually, in fact, it will move randomly here like this. So during its path, when it encounters electron in K shell, what it does? It will knock out that electron. It will knock out that electron. So the rough diagram, I'll put it. Here will bring an electron here. And this is the red color is what? The electron. K max, I'll write it. So there's a valence electron. There's a K shell LM. No, this fast moving electron can knock out this. When it knocks out, this it will dislodge it here. So then immediately what we get here, this electron weapon will be somewhere here, knocked out. And what about this electron will continue to move its path. It will have still more some energy left over. It will continue to move its path, and it will reduce. It will move with a reduced kinetic energy, K1 you call it. So here what we get, we'll get a vacancy, you know. And this particular electron weapon, what will happen to this electron? This electron weapon will be pulled by the accelerating voltage, or this will be taken by that accelerating voltage. No, there's a vacancies there in K shell. No, this vacancy now who can fill up? L. So an electron from L shell weapon will make a transition. it will make a transition from here. It will jump like this. Then when electron makes a transition from higher to lower orbit, what do we get? We get a photon. And that photon is what? K alpha X-ray we'll call it. And this vacancy which is there in K shell, so this is a vacancy I'll call it. Who can fill up that vacancy? Electron from higher orbit. When the electron from higher orbit will they jump, so what they do? They will again give out photon. Like this electron can create a vacancy in K shell or L shell or M shell, no? And when vacancy is created, that particular vacancy will be filled up by the higher orbit electrons. So along with this continuous spectrum, we also get a characteristic spectrum. We'll get a characteristic spectrum. Let me bring this graph. Try to see that one. So a vacancy created in K shell. Who can fill up? L. Then K alpha will be produced. What is the name of that photon? K alpha. A vacancy produced in K shell, if it is filled up by M shell. M shell means the electron. Electron will make a jump from here. Then give out photon. So then I'll get K beta. A vacancy produced in K shell. A vacancy produced in K shell. If it is filled up by N, I'll get K gamma. Next, if a vacancy filled up in K shell, filled up by O, filled up by K alpha, K beta, filled up by O, then we'll call that as K delta. Like that, what we'll give name K alpha, K beta, K gamma, K delta. Similarly, this fast moving electron can knock out an valence electron from where? In the L shell. Then if a vacancy is there in the L shell, how do that vacancy will come? Because fast moving electron can knock out innermost valence electrons. Now, if a vacancy is produced in L shell, it can be filled up by M, N, O. So then if electron makes a transition from M to L to fill up vacancy in L shell, then the photon name I'll call L alpha. Vacancy filled up in L shell, if it is filled up by electron from the N shell, then L beta, then L gamma. Like that, along with this, what we get is like, now a photon will come. Now the energy of photon depends on what? It depends upon the atomic number, the type of the target material. So shall I use what? Characteristic spectrum is. So how the curve will be now. So along with the continuous spectrum, what we'll get is, we'll get a characteristic spectrum. So if I plot the graph, this was a continuous spectrum. Where do we see K alpha, K beta like this? So where we have to show it now? How we have to show K alpha, K beta? How we have to show K alpha? So now I'll K alpha I'll show by red color. This will be K beta. This will be K gamma. Then next again, similarly, L alpha, L beta, this one. So I think K and L alpha, I'm showing that one. So this will be L alpha, L beta will get it. So this will be L alpha, L beta. This is called as K alpha. This is lambda K alpha, this one. We have to justify our answer. We have to justify our the graph also. Why only like this? Why the peak more? Why the wavelength will more? Lambda L alpha. lambda L beta. This is wavelength, and this is a cutoff wavelength, and this is the intensity. This is called like a characteristic spectrum. Sir, is it possible I want only characteristics? No. See, when do this characteristic spectrum will come? No, this is called as characteristic spectrum. That peaks what you see, no, is called a characteristic spectrum. And this is called as, the peaks are called as characteristic spectrum, and this is called a continuous spectrum. And now we have to justify all this, shapes, everything. Just notice I'll have water. Let's get into the discussion. Now, why that characteristic spectrum and why the graphs, and so how K alpha will be produced? Let's come for this one. If there's a vacancy in K shell, then who can fill up that vacancy from LMN? Then, if there is a vacancy in K shell, suppose that there are 100 vacancies are there in K shell. 100 vacancies are there. Not one atom in one atom, because it's a metal, no? Millions of atoms will be there. Let's assume that if there are 100 vacancies are there in K shell of the target atom, that 100 vacancies who can fill up? Some 80 will be filled up by L. Why? Well, because L is very near to the K, no? The probability of filling up vacancy in K is more due to L than M than N than O. A good example, suppose in a class, everyone wants to sit in first bench, no? I seen, especially boys, you what happen? You'll fight for first bench because they want to see things clearly. Then what I do? Anybody who is tall, I used to send them back. Only shorter one should come forward. So if the vacancy in the first bench is there, what happen? Who will fill up? The second bench person, what happen? The moment there's a vacancy there, what happen? The second bench student can fill up very easily, than third, fourth, fifth. It's a nature's phenomena. If the vacancy there, that happen. The second bench student can easily come and fill up because he's nearer. The same thing happens with the atom. If there's 100 vacancies are there in K shell, then in that 80 vacancies are filled up by the electrons making transition from L to K. Next, again, some around say like a 10 by the M. Next is some from say like some around 6 by the N. Some around by 4 by the O. So tell me, like, photons of which wavelength are more in number due to transition from L to K? K alpha. K alpha photons number are more. K alpha photons are more. So what will happen? Intensity will be more. Why the peak of K alpha more than K beta, K gamma? A vacancy in K shell, the probability of filling up vacancy in K shell is more due to L than M than N. That's why the intensity of K alpha is more. Simple logic, nothing is there. Why the peak of K alpha is more? If a vacancy is produced in K shell, then the probability of filling up vacancy in K shell is more due to what? L than compared to M or N. So the K alpha photons number will be more. So therefore the intensity is more. Similarly, a vacancy in K beta. So here, this one. Next again. What is this one? A vacancy in K shell. So what about the probability of vacancy filled up by M shell? Less compared to L. So the K beta number should be less. You can see here now. Then K gamma. What is the probability? Suppose this 80 electrons will jump from, I'll write it some number so that easy for you. 100 are vacancies are there. 80 will be from, 80 electrons will jump from L. Say some 12 from here. Say some around 7 from here. Tell me, like, 80, 12, 7. 80 photons, 12 photons, 7 photons. So intensity due to this particular wavelength will be more, no? K alpha will be more. 12 is due to K beta. this one k gamma. No, I'm not talking L beta, L alpha. Agree this idea? Okay. Now why the wavelength of k gamma more? You know, hydrogen spectrum. Which particular photon will have more energetic? I think the if a photon jumps from n to k, or m to k, or L to k, the photon which is generated due to transition from n to k will have more energetic, no? Then lambda should be less. So therefore, lambda k gamma will be less. Got the idea? Lambda k alpha will be less compared to lambda k alpha. The reason, because this the difference in energy of En Ek minus En, or Em minus Ek, El minus Ek, that delta E, you can look at that one. There will be more here. So like this open, we can uh, give the why the reason. Okay, next comes L alpha. Why the intensity of L alpha, K alpha? Why not both of same intensity? See, like to create a vacancy in L alpha means way it will be easy, because the electron, what happened? Why we are showing it this? Why not this L alpha? Let it be more. What do you mean L alpha? A vacancy in K shell. I think the way the probability of vacancy will be more, because when the electrons are passing through this, tell me, like, I think you look at the now radius of the shell. Here A naught, 4 A naught, 9 A naught. Of course, electrons are more. If you look at the probability of electron striking the K shell, is probability of this fast-moving electron striking the K shell is more than L or M. Any reason for that? In K shell there are only 2 electrons. In L shell there are 8 electrons. But look at the spacing, A naught. Here what meant 4 A naught. In a circumference of how much? In a circumference of 2 pi 4 A naught, 8 electrons. In a circumference of 2 pi A naught, 2 electrons. So look at the separation here. Definitely what happened? Here what happened? The probability of this fast-moving electron striking the K shell electron is more than L shell. Got this? So since vacancy in K shell will be more compared to vacancy in L shell, so the intensity will be definitely less. Again, why L alpha, L beta? Again, same reason. If vacancy in L shell is there, who can fill up more by M shell? There's the thing. By why, sir? Why K alpha, L alpha? What is the reason for that? Because the probability of creating vacancy by fast moving electron in K shell is more than L shell. The reason for that, again, the radius A naught. This will be 4 A naught, 9 A naught, 16 A naught. Then it will not encounter much collisions. It can encounter collision because they'll be closely packed. That's the reason what we can give it. This called like a characteristic spectrum. Why characteristics? Because it depends on material, no? Why this wavelength this much only? It depends upon that energy level, and energy level depends on atomic number. So therefore, I'll call characteristic spectrum. Next question comes: any electron can produce, any fast moving electron can it produce characteristic spectrum? The answer is no, because to go and knock out what happened, it needs some energy, no? So therefore, there's some threshold energy is needed. So I'll decrease the accelerating potential. 10 kilowatt. I see continuous spectrum. So when the characteristic spectrum will come only after some threshold voltage. So when I plot curve, there's one more last very good information there. I'll conclude. Then we'll go to Moseley's law. Now look at this. So there's the intensity. There's a wavelength. For all accelerating voltages, will I get? The answer is no. So here is what I can notice the peak. K alpha, K beta, L alpha, L beta. Then again for the same material, will you show K alpha, K beta some other place or there only? I think K alpha, K beta doesn't depend on accelerating voltage, no? So we have to show it at same place. So we'll produce a line. Not visible. I'll make it. I think this line will be visible. You should not shift that particular thing. It should be, so if you vary the accelerating voltage, it should not change. Where is the K alpha? It will be there only, that one. Getting the picture, this is very important. This is like for, I don't see anything. I don't see characteristic spectrum. So some rough it is. So why we, only continuous spectrum, both continuous and characteristics. Now, why it happens? Because see, to produce characteristic spectrum, what should happen to the electron? The electron should penetrate more deep into the atom. It needs more energy. It needs more energy. So by the time what when it reaches the K shell, if not having sufficient energy to knock out, it will not generate, no. It cannot knock out K shell electrons. Then we don't get characteristic spectrum. So for all accelerating voltages, we don't get characteristic spectrum. Only some threshold is there. That depends upon the material. So like this, what happened? We will just put it that one. Okay, there's some information is there, so you better remember. Very useful for you in exams. Okay, now what is that K shell? So if you see the SU Alma, he has asked some questions where the energy of like this is telling that one. This is, I think this is the correct way of energy band diagram. This is a EK. What do you mean by lambda K alpha? Lambda K alpha, this is called like a lambda K alpha. Then what is lambda K beta? This is the lambda K beta. This is called as lambda K gamma. What is L alpha? L alpha will be this much. Then lambda L beta. Now, when a vacancy is created in an atom, when an atom with a vacancy in K shell, it will have this much of energy to create this much of. So, so what you can say that to create a vacancy in a K shell, so what happens? The electron needs energy. What is this EK you're drawing? This would be the energy of the atom. And when that particular vacancy is filled up by an atom, when electron from the L shell. So what happened to where the vacancy will go? The vacancy will go to L shell, no? Then what happened? The energy of atom with vacancy in L shell will be this much here. So you find a little bit difficult. So what is the meaning of this graph? I'll just give the explanation like this. There the vacancies there. In the K shell. Who can fill up? Yes, definitely the electrons. Just understand this diagram. It will be very easy for you, that energy diagram. Possibility of asking. There are 8 electrons are there. So what is the energy of this atom now with vacancy in K shell? 69.5 electron for some substance. Now same this, now this vacancy will filled up by ohm. Red color dot is what vacancy. This vacancy will fill up from L. So now this vacancy will be filled up. Where the vacancy is there and putting that electron back. And now where the vacancy has come, the vacancy has now come in where? In the L shell. Got the dot is what? The vacancy. How many? 7 electrons will be there, no? Now when you measure this energy, this is K shell, L shell. Now the what is the energy of this will be 11.5 electron volt. Okay, are you getting now? So when the electron makes a transition from L to K, L shell to K shell, then the energy of atom what happened? From EK it will become EL. So where do that energy of atom gone? Convert into photon, and that is what lambda K alpha. So there may be a problem for you like this energy level diagram. So what is this? What we should call? Energy of atoms with vacancy in respective shells. When there's a vacancy in K shell, it will have this much of energy. When vacancy in the L shell, the atom will have energy of atom. Now this is something very important. It's there in SU Verma. He has put this in the form. He has explained everything with the help of this energy level diagram. Other books they avoid it, but I think this is a concept here. So how do you calculate this energy? I think it's beyond our reach of Bohr's atomic model. So in exam they will definitely give this information. So how to calculate lambda K alpha? How to calculate lambda K alpha? Hc by lambda K alpha should be equal to what? Ek minus El, finish over. Similarly, I want Hc by lambda K beta. Then how to bring this? K beta, this should be equal to Ek minus Em. Even if they give information, okay, you can take help of. This will be much easier. And the maximum information will be like this only. Got the idea, no? So therefore, why there is no characteristic spectrum? Because to knock out innermost valence electrons, the electron occurrence should have sufficient energy. By the time it reaches here, to produce vacancy in K shell what happen, the electron should come out this much of energy. Then you can produce that particular thing. So therefore, to knock out innermost valence electrons, first it should penetrate more, no? So by the time it penetrates here, what happen? Most of the energy will be lost in the form of heat. So therefore, for lower exciting potentials, we don't see characteristic spectrum. We see only at certain level that one. It depends on material again. For different target materials, the exciting potential at which the characteristic spectrum will be obtained will be different here. Okay, this data is very important. Do remember this graph also very important. Not there in books, but for different exciting potential, this lambda K alpha will not change. Lambda K alpha depends on what? Target, not on V naught. So one of the tabular column, it's available in book. I just brought it. So like this information is available. So possibility of asking. So from SUM, I think it's one of the book is available. I just picked up here. For tungsten, vacancy in K shell, 69.5. For molybdenum, what happens if there is vacancy in K shell? What is the energy in kilo electron volt? I think 69.5 kilo electron volt. Now come for this. So there's the information. Just no need to memorize. I just brought an idea that one. So now suppose say that if you are using molybdenum. I think you need less accelerating voltage to produce characteristic spectrum. Got the idea? If you're using tungsten, you need more accelerating voltage to produce this characteristic spectrum. Able to make it out? If Ek is vacancy in K shell, if the energy of atom with vacancy in K shell is more, then you need more accelerating potential. That's the meaning of this. Okay, this is one way of producing lambda K alpha. Now, using